Yeah, okay, so thank you for the invitation. So I will talk about energy. And maybe one important thing to mention first, since it was mentioned that we take a little bit of energy for granted. What you see here is for different countries, the energy consumption per capita is function of the GDP per capita. So basically, and you see that there is a very clear correlation. And so that means basically that developed countries are actually consuming more energy. If we want to be developed, we need more energy. So energy is basically, like the food for our infrastructure. Now, if you look at Switzerland, what's interesting is, very often we only speak about electricity, but electricity is only like 26% of the energy that we consume. The majority of the energy that we consume comes from heating, mobility, and industry, and this is for the majority fossil fuel that we import. And when we are talking about energy, we cannot talk about energy if we don't talk about the energy trilemma, right? An energy trilemma has 3 pillars, right? So the first pillar is environmental sustainability. Okay, so what is sustainability? It's a little bit in this bubble. Again, also here, this tunnel vision, we focus very much on greenhouse gases, so CO2 emissions. But in reality, sustainability includes also how much land we need to produce a kilowatt hour, how many materials do we need, how much waste we produce, and so on. So what if we focus on CO2 emissions, what you see is that, if you look at the CO2 emissions per produced kilowatt hour, of course, the fossil fuels, they have high emissions. We know that. This is actually why we want to phase out them. But then if you compare nuclear, hydropower, solar, wind, they're actually the energy systems that have very low emissions. Actually, none of those systems emit CO2 during operation. This CO2 emission comes from the life cycle because you have to mine the materials, because you have to build the plant, the solar panels, the wind turbine, and so on. And now what you see on the right side is actually the CO2 emissions per kilowatt hour in Europe. Green is good, so low emissions, brown is bad. And now you can already see which are the good countries, including Switzerland. So Switzerland is already one of the few countries that has a decarbonized electricity production, not energy, right? Still a lot of fossil fuel for heating and industry and for mobility, but not for electricity. And so what are the good countries is Iceland, Norway, Finland, Sweden, France, and Switzerland, right? And okay, so if we look at, what is the electricity mix of these countries, we will see that all these successful countries as a mix, renewable plus nuclear, with the exception of Norway and Iceland. However, Norway has 90% hydropower, and Iceland has 70% hydropower and 30% geothermal. And I always say, we cannot build mountains, we cannot build volcanoes. This is actually what they have in Iceland. And so these models we cannot export in other countries, but the model that can be actually reproduced everywhere is the model renewable plus nuclear. What you see on this picture is also very interesting. So basically every cloud of colors is one country. So you see Germany, Poland, Italy, Switzerland is here, France is in blue. And then every point in this cloud is 1 hour of last year. And what's interesting is that you see that there is not a single hour in the year where Germany is better than France. I don't say the same, not even the same, right? So basically, Germany always emits more than France, and so on. And so why is that? And we have to look at actually how electricity is produced in Germany. So what you see in this picture is November, so winter month. The black line, this pointer is not really, okay, so this black line here is how much electricity is needed. And then what you see with the colors is how is this electricity produced. And now you see, okay, in winter, like solar is not so much. They have a lot of wind, but wind is weather dependent, so sometimes is a lot and sometimes is very little. And so then what do they have to do? They have to produce a lot of their electricity with gas and coal, even brown coal, which is actually the bad coal. And then what you see in white is the imports. So they don't manage to produce enough, so they have to import. Now look at France in the winter. They have a huge amount of nuclear, and then they have a mixture of renewable, hydro, wind, solar, and so on. Black is also what they need. So what you see is that they always produce more than what they need. France is the top exporter of electricity in Europe. They export all the time, in winter and in summer. So they export around net export 80 terawatt-hour per year. While Germany imports net 30 terawatt-hour, and Italy even more. And this is summer. So you think, okay, summer is going to be better. Yes, a little bit. But you see, I mean, still a lot of imports for Germany, also in summer. A lot of solar. However, the sun is not shining at night. The wind is not always there. And so then still, even in summer, gas and coal. And so this is actually why there is not a single hour in the year where Germany is, I don't say better, but at least equal to France. And then you see France in summer, so they have a little bit more solar, of course, because the sun is shining more. And now, so in the energy trilemma, so I discussed the greenhouse gases, and okay, I cannot discuss all these bubbles, but very important is the raw materials. And what you see on this picture on the right is the mining intensity. So basically, how many kilograms of material we have to move in the mine to extract the minerals and other material that we need to produce 1 gigawatt-hour of electricity. And now everybody, when he thinks about nuclear, thinks, yeah, we have to extract uranium. Very true. And so for nuclear, you see here in gray is the uranium that has to be extracted from the mine per generated gigawatt hour. But you see that for the other one, solar, wind, onshore or offshore, you have to move material in the mine even more than for nuclear. And why is that? Because, okay, in nuclear, you have a very, very high energy density. So we have it's the highest energy density that we have on the planet. And so this is actually why per unit of generated energy, you need to extract less materials, right? Okay, then there is the energy security, right? So energy security means, okay, do we have a reliable energy supply? So do we have this energy when we need it? And are we resilient to shock? So, if there are some geopolitical changes like the Ukraine war, and now, like what's happening between China and US, are we still safe? Can we still produce the electricity that we need? And now, if you look at the risk identified for Switzerland by the Federal Office for Civil Protection, what you will see is that the event that has the highest probability, and not only that, the highest damage in money, it's actually a shortage of electricity. It can happen once every 30 years. And there are recent examples, not in Switzerland, but for example, in Texas, February 2021, there was an extreme event. There was a windstorm, a snowstorm for 10 days. They had a blackout for 10 days. 250 people died. People literally died frozen in their own houses or in the hospital because there was no electricity for respirators, for dialysis machine. Cost $300 billion in damages. California, September 2022, they were half an hour away from a complete crash of the grid. They sent SMS messages to all mobile phones in California to ask people to shut down everything they could, washing machines, air conditioning, and so on. They managed. And then they decided to save the last power plant that was supposed to shut down 3 months later, because California has done exactly the same what Germany did. And they said, no, we cannot shut it down. And so then now they invested $1 billion to extend the lifespan of this power plant by 10 years. So, again, like, let's buy some political time. And then Spain, you heard last year, right? So worst blackout in modern history in Spain. Initial cause was a loss of solar generation, but that was not really the problem. The problem was the grid was not resilient. So a perturbation led then to a cascade effect where basically then everything else shut down. Now, what is the issue also with the energy security is dependence from geopolitics. So what happens if you look in this plot is that the mineral intensity of the new generation capacity is increasing. So basically we are phasing out fossil fuel, but we need now more materials to build the solar panel, wind turbine, batteries, and so on. And this material, as I showed you before, have to be mined. And where are those materials? And now here you see what is a little bit scary, right? We have to extract the material from the mine, and then we have to process this material. And now you see that color violet, this is China, and you see that China dominates these minerals and material either in the extraction or in the processing of the raw material. But dominate means you see more than 80%. As a matter of fact, 96% of the solar cells today are produced in China. And you see 90% of the solar panel that we use in Europe are coming from China. And with the current geopolitical situation, I'm not sure. Then we saw also the geopolitical instability due to the war in Ukraine, right? So the increase of gas and electricity prices recognized the importance of energy security. And for example, Germany, that was strongly dependent on the gas from Russia in 2022, within the first 9 months, they had to pay 440 billion euros for a temporary measure to mitigate this effect of the energy crisis and to try to decrease the electricity prices for industry. Otherwise, they had to shut down everything. Right? So it's important. So energy security is important. And then energy equity. Energy equity means, can we afford this electricity? So is it payable? Only the rich one can have it, and then everybody else cannot, right? This is one thing. And then the second one is it cheap enough to keep our industry competitive in the global market? Because if our energy is expensive, then our industry are going to produce too expensive products. And now you can look at the picture there. So the cheapest is China, followed by US, and then where you see the dark expensive color, Europe. And you see it here better here, right? So in industrial electricity prices last year, UK at the very top, then Italy, Germany, Poland, France, and then at the very bottom, US. And you see there is a factor, 3 or more expensive here. And then China is even below US. So how can we compete with US and China if our energy prices for industry are 3 or more times more expensive, right? So this is what we have to consider also. And now here is actually the plan for Switzerland. So right now, the plan is to phase out nuclear. And so if you look at 2050, and now in these numbers, this boom of artificial intelligence is not yet included. But basically, if we want to electrify industry, eating, mobility, we will need at least an additional 25 terawatt hour per year on top of what we produce today. And then by 2050, we have to say goodbye to our nuclear power plants, which now produce 23 terawatt hour per year. So that means that in addition to the 25 terawatt hour, we need a 23 terawatt hour of alternative to nuclear. This is actually why I always say, if we don't replace the nuclear with the new nuclear, we make our problem double more challenging. And now, okay, there are many studies, okay? I'll take just one, because it's the latest from last May, right? From the Department of Energy, several university and research institutions in Switzerland. So what do they say? Okay, so if we want to do this 2050 scenario, and we want to also phase out nuclear, we will need at least 28 terawatt hour of solar, 13 terawatt hour of wind, and then plus biomass. And then, of course, because these are weather dependent, so they are not dispatchable, we will need to increase imports in the winter, and we will need also some gas as backup and so on. What does this mean, 28 terawatt hour solar? It means that we have to have 4 times more solar than we have today, and 80 times more wind than we have today. And in picture, because, I am an engineer, and when I see these bars, 20 terawatt, so much, and so on, okay, I always say, but in practice, what does it mean? And okay, so in practice, I take as a unit 12 terawatt hour, because this is actually what is produced by one power plant. So the power plant that has been, for example, in operation in Finland since 3 years, and another one equal to this went in operation in France last year. This produces 12 terawatt hour a year. If you want to produce the same electricity with free field solar, you would need 1,090 equivalent of NALP solar, which is one of the AXPO free surface PV plants, or you would need 1,363 wind turbine of the large one, so the 200 meter tall, which are 70 meters taller than the cooling tower of Leibstadt. And so now you see, we need a 13 terawatt hour wind, so that means, a little bit more than 1,363 turbine, and 28 terawatt hour PV, so more than double this 12, right? Which means that, if we calculate, it will mean something like 8 bifacial solar panel, the same used in this NALP solar, per person in Switzerland, assuming 9 million people, so including babies, right? So each of us, 9 of this solar panel. And of course, like the question is, first of all, for me, is can we do it? Can we build so much in 20 years? Because this is actually what we have, right? And then of course, we have also to build the grids, and the grids is even worse because you need permits and so on. It takes 10 years, like to have a grid project and so on. And if you look then at the conclusion of this study, you still need, you need subsidies. There will be increase of electricity prices if Europe does not export to us everything what we need. We need gases backup and so on. And then, also important statement, that if we need also synthetic fuels like hydrogen and so on for aviation, for mobility, but the production would require solar power plants on a scale that cannot be built in Switzerland because, we have limited land. If there is one thing that we don't have much here in Switzerland, is land. And so when we are looking at energy system transition, very often, we look at a picture like this, where we go, from this concentrated, monopolized energy system to the one of tomorrow with the many small power plant, with the solar panels on the roof, decentralized, we now can, as households, can buy and sell and so on. And unfortunately, there is this very polarized views, like the old and the new, right? And in reality, if we think about it, we have a mix of users. So, we have households and companies that have variable load, but then we have industry that needs electricity 24 hours a day. And this industry cannot afford to have electricity coming from weather-dependent sources. So that means that in reality, we should have a hybrid grid. So we should have a mix of decentralized and centralized, where you then will have different clients for the different part of the grid. And so now, okay, for nuclear, something that I would like to mention is the new technologies that are coming are small modular reactors. So these are smaller reactors. They will cost less because they are smaller, so they produce less electricity. It's not that the electricity will be cheaper, but at least the machine is cheaper. So more people, more companies can invest in those. And they're not sci-fi. So Russia and China, of course, they are far ahead as everybody else. So they're already operating this power plant. Nuclear, Europe is waking up now, and the US finally woke up. And now in the US, they have a lot of plants which are either in construction or where they asked the construction license, and so they are actually actively waiting for the construction license. So, for example, the liquid metal reactor from TerraPower, the company from Bill Gates, so Microsoft, is waiting for the construction license at the end of this year. The same for X Energy, which is getting money from Amazon and from Dow Chemicals. So now we have this bottom up, if you want. So basically you have clients that do the direct orders and so on. And so this is actually what's coming, right? And then we see also bottom-up examples in nuclear in Europe. So for example, here I mentioned two. One is Finland. They are developing a very small reactor underground that is only meant for district heating. So basically, it will mean it's a very small reactor. It does not need a turbine because it will never produce electricity. It's always only to produce basically hot water to distribute to a grid. And now the thing is, the grid is already existing. So the district heating grid is already existing. They just have to change the heat source, right? Here in Switzerland is the opposite. So we have a district heating grid connected to Betznau, and Refuna is the company in Aargau that managed this. And now, unfortunately for Refuna, Betznau will be shut down in 4 years. And so they looked for alternative, and the alternative of Refuna is wood pellets. And they will need 38,000 tons of wood pellet per year, transported by 1,700 trucks per year. So much for the environmental friendly. What you see, the other example is Norway. Here is also very interesting bottom up. So here is basically a group of 10 companies in 10 municipalities, together with the 10 municipalities that went to the government and say, yeah, you don't have nuclear, but we want it. So please make sure that we can do it. And they identified 4 sites for this small modular reactor. And so basically now is the process, is a very bottom up process. So now my conclusion, personal opinions, of course, because I have to say I'm not an expert of energy system. I'm a nuclear engineer, but I just look at the systems. And I said, okay, bottom-up projects are very suitable, very easy for small plant sizes. And for example, for renewable, where the plants are always small, solar and wind, we have seen several examples successful here in Switzerland already. Now, the bottom-up in nuclear is more complex because the plant is bigger, you need more money, the process is more complex. So for this, you need a consortium. For example, right, you would need cantons, the municipalities. The interesting thing with nuclear is that municipalities that have nuclear, they are very much in favor of nuclear because they are familiar with the technology, they are not afraid of it. Because, of course, if you have a nuclear power plant, you have a lot of jobs, not only in the power plant, but in the municipality, because now there are a lot of people working there, hundreds of people, and so now you need new supermarkets, air salon, and whatever, right? So basically, there is a lot of job creation for the community, and there is, of course, tax they're coming. So then the tax rate in these villages is smaller because of the power plant, right? And so basically, in fact, if you see here in Switzerland, all the villages who already have a power plant, they already said, we want the next one if there is one built here in Switzerland. And then, you can make a consortium, for example, with pension funds, because pension funds have investment long-term, while companies typically want to have investment very short-term, right? A power plant has a lifetime of 80 years, so you need these long-term investments. Or you can have investment from companies who are interested in baseload electricity, right? So if you can put these groups together, then you can have a bottom-up approach, like, for example, they had it in Finland. In Norway. And now the issue is, it has to be considered this, my opinion, of course, I'm not an expert, but bottom up in a complex energy system, skewed even with subsidies like it is right now, not only in Switzerland, but also in most part of Europe, create then not only fragmentation, because, okay, now you have many pieces, but, we need a global system that works together. And then it can have also counterproductive results because, we have seen, for example, in Germany and California, where they've installed so much renewable, but not enough batteries and backup, where now there is too much sun production when the sun is shining, and so now this power plant has to be shut down, or the electricity prices are negative, which is never good for producers. And also the bottom-up does not work with all parts of the systems. We need the grid, so you cannot build decentralized many systems of solar batteries and so on if nobody then builds the grid, right? But the utilities typically don't do that. So this needs a top-down approach, right, or integrating approach. And so this is actually why bottom-up in energy system is tricky, right? And now, okay, so this is my very last slide. So we need this top overview as well. So it cannot be just bottom-up. It has to be coordinated. Then we have to recognize that there are different and at time contradicting drivers. Like there is a grid inertia, there is a grid stability. So the engineers, to avoid what happened in Spain. But then there is the politicians, and they are connected to the voting cycles. And then there is the short terms versus long-term investment. So different companies, they look a different way at investment. As I mentioned, there are companies that are interested in electricity 24 hours a day, and they need security of energy and also affordable costs. And then there are the grid operators that say, hey, if you want to build a grid, you have to tell me in advance and you have to give me the money, right? And so that means that we need some kind of global forward thinking, right? So not just individual project, but individual project within a system. Then, if you look at what I mentioned about the energy trilemma, I think it's very crucial that we diversify for many reasons, right? For geopolitical issues, so that if something is affected, the other one is not affected, and so on. Or if the weather is bad, something else is working, the weather and so on. We have more flexibility. And of course, to me, it's important that we promote a mechanism for collaborations, because right now there is always this constant story of renewables against nuclear. There is this fear, if there is money for nuclear, there is no money for renewable. But as I think I showed to you, the challenge is so big. There is actually a place for everybody. I don't think there is no silver bullet. We cannot do it alone with nuclear. You cannot do it alone with renewable. We need everything. Okay, and then this is the thing, is that we have to identify mechanisms to cope with the not in my backyard. And we see it also here in Switzerland, right? That people are against everything. They're against the alpine solar. They are against the wind turbine. They're against nuclear. They're against the grid. And then at the end, we don't build anything, right? And so how to do this, right? Okay, maybe sharing of revenues with host municipalities, maybe rebates of electricity prices for the communities that are hosting this thing, local ownership and so on. And then this is my very last point. we are talking about climate change, and we design systems based only on weather-dependent energy sources. Good luck with that.